Hey everybody. Today, you can see the title up at the top. We're going to talk about similar triangles. Now, this topic is a review topic for us, but it might be something that we have varying levels of experience with, exposure with. I'm going to talk about it today as if it is a review topic. Then we'll kind of formally get down a little bit of theory. We'll talk about how to recognize corresponding sides a little bit, and then we'll just talk about labeling some triangles. But for today's topic, I want to jump in as if we already have a bit of a background with us. So let's jump in and take a look at the problem that we have in front of us. I've given you two triangles, and I've asked you to find the missing sides. And maybe you can look quickly on the screen and you can notice that, hey, you've got side A and you have side B. So those two sides on our smaller triangle, those are the two sides that we're looking for. So, where I want our eyes to go to first, and I'm just going to highlight a little bit that my big triangle has an angle of X, and I notice that my smaller one has the same angle. And if I relatively quickly around that triangle, there's my good old-fashioned angle marker, and I've got the same angle in my smaller triangle, another two angles. Well, if we go pretty quickly, you'll notice that that third angle is also equal. And so what we find is we actually have two triangles with the same angles in them. Now, we look at those triangles and clearly they're different sizes. But the fact that they have three of the same angles in them means that we have triangles that are the same shape. They're the same shape, they're just different sizes. And that's what we're talking about when we refer to similar triangles. Now, what does that mean with regards to side lengths? Well, it means that in order to maintain the same shape, the same angles in between, if I went to shrink one of the bigger sides triangles to try to shrink it to the length of the smaller one, if I didn't change all the sides the exact same way, then I wouldn't maintain those same angles. I would end up changing the shape. So take a look at the sides that I've highlighted with blue there. Now what I'm going to do is I'm just going to erase that blue marker that I just put on, but I want you to take a peek at that and notice that those two sides are between my X angle marker and my formal angle marker. If you want to go with the colors, they're between the purple and the red. Because those are the sides between the same two angle markers, those sides, 8 and 2, would be considered corresponding sides. What that means then is the way that I change 8 to get to 2, hopefully we see that I would divide that by 4. I would shrink it by a factor of 4. I would have to do the exact same thing to all the other sides of my big triangle in order to maintain those same angles, that same shape. I could go the other direction. Look at my blue arrow again. I could take my 2 and I could blow it up. I could enlarge it by a factor of 4, multiply it by 4. And I would then produce the bigger triangle. But for me to produce that bigger triangle, I would have to do the same thing with all the sides. Otherwise, I would change the shape. That's what we're talking about when we say similar triangles having the same shape means that their sides must be proportional. If their sides don't relate to each other the same way, then I've changed the shape. So let's zero in on that blue again, because I'll notice that I do know the actual dimensions of those corresponding sides. One on the big triangle, one on the small. Okay, I'm going to delete the circle around that B, and I'm going to find A first. And the only reason I'm going to find A is because alphabetically A comes first. There's no other logical reason. So please do not feel like you had to find A first. Not at all. I can take a look back up on my big triangle and try to find the corresponding side that would match up with A on the smaller triangle. Well, A happens to be the side between the X and the O angle marker. So its corresponding side would have to be the side between the two same angle markers, and you notice that that's 12. So if I just get rid of those red arrows, and I focus in on that A then, I know that if I was to create a ratio, I could figure out how I change those sides. So how could I start it off? Well, I could very logically do something like this. I have to take the 8 on the big triangle and change it into the 2 on the smaller triangle. That means that I would have to divide it by 4. If I struggle to see that factor change, I could always just calculate it. And I could take the bigger, divide it by the smaller, and get my 4. Well, what that tells me then is I would have to divide by 4 to move from the larger triangle to the smaller. So if I can't see what that factor change is, I can calculate it. You can see that in the blue. Well, the other way we could deal with that then is we could logically go through and change the sides in the same way. Well, if you look beside my blue arrow again, I could divide by 4 to change from the big triangle to the smaller. What that tells me then is I always have to divide by 4 in order to maintain the shape. And so we could, through some really sound reasoning, immediately just come up with that my side A would have to be 12 divided by 4, and we could just calculate it to a 3. Nice. Okay, what I just did there in the red and the blue is something that works out really well when our factor change. That 4 number is something really easy to find. Okay, what I'm going to do is I'm going to imagine, just doing something different here, I want to imagine that in order to find that side length B, it wasn't just divide by 4, or at the very least, I should say, we didn't find it that easy to find that 4 value. So I'm going to go through this as if we were stumped a little bit. Okay, how could I tackle it? Well, what I need to do is find 2 sets of corresponding sides where I know both dimensions. Or 1 set, I guess. Take a look at my blue circled sides. I know that 8 on my big triangle has to become 2 on my smaller triangle. Well, if my triangles are similar, and I can see that they are because they have the same 3 angles, then I know that the way I change from one side to the other one has to be true everywhere in my triangle. So if I look back up on my top triangle, since I'm looking for the side that corresponds with B, that would be the side between the red angle marker and the O angle marker. That's my side of 15. So what I can do is I can then state that the way 8 divides to 2 has to be the same thing as the way 15 divides to B. And what you'll look at in that purple is me setting up a ratio equation. Okay, if we're good at solving that equation, well then this just becomes a mechanical problem for us. If I need to solve for B, then I need to get rid of my divide by B, which means I'm going to multiply it out. I'm hopefully going to reduce the left side because 8 divides by 2 evenly. But again, remember, we're just talking about this as if it wasn't so nice and neat. So what I could do at that same time then is I could get rid of my divide by 2 and multiply by 2. That would give me the next line in my equation of 8b equals 30. And now I've got the easiest of easy. How do I go through and solve for b? Well, I need to get rid of my times by 8, so I'm going to divide by 8. And now I get that value, and I can reduce it to lowest terms. I can divide top and bottom both by 2, and I get to 15/4, and I am good. There you go. Take a look in red. That is a way where we can use a nice, neat factor change to simply multiply or divide to move from triangle to triangle. Or if it's a really ugly factor change, we could go through and we could just simply say, hey, I'm going to set up a ratio equation and solve. Okay, I'm hoping that that brings back some of our review stuff. What I want to do now, I want to go through some problems just a little bit quicker, and I want to talk about maybe some other elements to us dealing with similar triangles. Okay, so what you see on the screen now, there's our diagram in B. I'm just going to highlight, if you notice in what I've highlighted in purple, we've been told that those two sides are parallel. Remember, that's what those arrows mean. Okay, for us to take a peek at that, we've been asked to do the same thing again. We need to solve for side X and solve for side Y, my missing sides. Okay, you take a look at that diagram, though, and an issue might become, okay, are those similar triangles? With a little bit of thought and a decent amount of background on some angle theorems, I'm hoping that we could say yes. Okay, the whole component to this is those purple parallel lines. I'm not even going to put anything else in other than address those purple parallel lines, because what should be coming back to us is some of our parallel line theorems from grade 9. I'm going to highlight one of them in particular, our good old Z pattern. I'm going to do it in green. If I was to look at this parallel line and this parallel line, hopefully you can see those highlighted in green, and the line that intersects them, there is our fancy word for a transversal. What I just created was a Z. And Z pattern says that the angle contained must equal the angle contained. Formally, there's our alternating angles. So, without even knowing what that angle measurement is, I do know that those two green angles have to be equal because of Z pattern. Okay, I'm going to delete all that green just so our diagram doesn't become too complicated for us to see. I'm just going to fix up that purple arrow a little bit. But I am going to mark on that diagram that angle green equals angle green. Okay, I'm hoping that you can see, without me really spending a whole lot of time on it, that you also have another Z pattern. Just go in the other direction. And that would mean that the two contained orange angles would have to be equal. So I'm going to get rid of that orange. And as I get rid of that orange, I'm also going to draw in my orange angle and my orange angle. Those are equal. Now, if you don't have multiple colors like I do, then maybe what you do is you put in that double angle identifier. And that's a way to show that those two being different. Okay, for a number of reasons now, we should be quite comfortable to say that this angle that I might mark as in like an angle O has to equal that angle, angle O. You have multiple ways to get there. I'm hoping we remember that all three angles inside of a triangle have to add to 180 degrees. And so no matter what the green and the orange were, if we were to try to find the third angle, we would simply add them together and subtract from 180. We would find that we would get the same thing in either triangle. Or you may remember, if you take a look at the location of those, that is one line intersecting another line, And what that creates are opposite angles. And also from grade 9, we should know that opposite angles are equal. So whatever reasoning we come to, hopefully we can see we do have similar triangles because of our parallel lines and intersecting lines. Okay, I'm going to get rid of my red circles around those missing sides just to clean up our diagram and to highlight the fact that what we have are similar triangles. Triangles that are the same shape, just different sizes. What makes this one a little more difficult? I think that we may have some people that if I asked you right now to go and try to find what is the corresponding side on the other triangle to side X, that they may think it's 6, just because of some optics, those sides are both on the top of the shape, if you want to think of it that way, and incorrectly, we would put those two sides as corresponding sides. We have to be very careful, and this is where our angle markers come back into play. Look where side X sits. It sits as the side between the orange angle marker and the blue angle marker. And so if I wanted to know what was the other corresponding side on the other triangle, I would have to look for the side between the orange angle marker and the blue angle marker. And you notice that's the side 7. X and 7 represent corresponding sides. Okay, I'm going to leave my red arrows up there for a second, and we're going to solve for X. The same thing, we'll solve for X just because alphabetically it comes first. By no means do we have to. My advice to you would be, take a look on your diagram and go on the hunt for two corresponding sides where you know both of those lengths. They're not unknown, you know both. And maybe you can take a peek, and between the green and the orange, you can see that the 10 and the 15 are both corresponding sides. So what I can do then is I can go ahead and I can start to build my ratio equation. So my advice to you would be, if you were going to build that, then maybe let's start from the standpoint of what are we looking for? So if we notice, off to the right, I'm going to build my equation. If I was looking for side X is on my smaller triangle. I want to know, how does X change into 7? And maybe I create my ratio that way. Well, what I could then do is I could make sure that I know that that ratio change has to be true throughout the triangle. So if I went to go and build my next ratio, hopefully we're good that we could see that it has to match the way 10 changes to 15. Now, there are some common mistakes here, and I want to highlight the most common one, but what you see in red is correct. Okay, what could the incorrect ratio equation be? Well, it could have been this. Now, maybe you start to go like, okay, well, why is that wrong? How could I avoid that mistake? And this could be a nice, easy way to do it. What I have to make sure that I am always doing is relating one side to its corresponding side the same way throughout the triangles. So if you take a look at my red fraction, x over 7, now I want you to look back inside my triangles. If I called my small triangle, triangle 1, and I called my big triangle, triangle 2, then what I'm setting up in my red equation is triangle 1 on top of triangle 2. You look at my red, x is over 7, so triangle 1 is over triangle 2. If I mistakenly then wrote that fraction, maybe you can see that 15 over 10 would now be triangle 2 over triangle 1. I don't have consistent fractions. I'm not comparing the same sides in the same direction. So what I can do is make a quick little statement like I make in pink. That might remind me, okay, I'm always going triangle 1 over triangle 2. That way, I do not write down 15 tenths. I am focused on the fact that I need to put my smaller triangle, triangle 1, on top of my bigger triangle, triangle 2, and now you set up your correct equation and you're good to solve. So, to get rid of a divide by 7, I need to multiply by 7. I'm going to get 70/15. Maybe you didn't tackle it that way because you didn't want to blow stuff up first. Now, just to have to reduce it, well, 70 over 15, I can divide top and bottom both by 5. Hopefully, we're not writing down that green. We can just see it. And if you were to divide 70 by 5, you get your 14, and 15 by 5, you get 3. There's my exact length of x. Okay, there is another way to solve this, and I do get a little fearful about showing you this, but more knowledge is better. Let's tackle this one a different way. Rather than me going through and putting all of one triangle on one side, the top, and then all of one triangle on the bottom, I could end up going through and thinking about it a different way. I want you to take a look, and in blue underneath my diagram, I'm going to think about it as how I change it. So I can put my corresponding sides on top and my corresponding sides on bottom. What do I mean by that? Well, I could set it up this way, that x has to change to the number of 7. My x on triangle 1 has to change to 7 on triangle 2. And it has to change the same way as my 10 on triangle 1 equals my 15 on triangle 2. What I've done instead is I've sat there and said my first fraction must be all triangle 1 and my second fraction must be all triangle 2. Some people like to logically think it through that way. It really hammers home the point about corresponding sides. If I do that, then pretty quickly, to get rid of a divide by 10, I'm going to multiply by 10. There's my 70 over 15. And you notice we're just coming in on 14/3 in a different direction. So hopefully not too bad. Okay, I think this gives us a moment to just pause it real quickly and try to give it a shot on your own. I would like you to go through and try to come up with the exact value for length y. Okay, pause it now. Okay, we're back. I'm going to just shift everything over and shrink it a little bit so that I can put my solution way over here on the right. I'm going to do maybe the second way we went through, the blue solution, just to give us another way to tackle it, some more variety. What I could say is, if I am looking for side y, well then side y on triangle 1 has to become side 6 on triangle 2. Both those sides are the sides between the green angle marker and the blue angle marker. But the way I change those sides has to be the same way as 10 on triangle 1 compares to 15 on triangle 2. Now, I really don't like having that equal sign floating around up top that way. It drives me nuts. There's better form. Okay, for us to solve it, I'm not just going to multiply out my 10. I'm going to show a different way too. That maybe what I do is I take a look, and on the right side, I end up with 6 over 15 times by 10. Now, I could go through and reduce that fraction. Like, A 6 could divide by 3 evenly, and so could a 15. And then a 5 could divide out from my 10, and we could come in on a value of exactly 4. And there we go. Just a different way to cross-reduce as opposed to multiplying and then having to reduce at the end. Okay, I'm hoping that that gives you a really good run-through with similar triangles. Really good run-through. Your goal is to be really solid with your similar triangles before you walk into class next day. Okay, there's 2 other things that I want to talk about within us working through this, but let's get down some formal stuff. What you see on the screen right now is something I would like you to get down formally. And it's just all the stuff that we've been talking about up to this point, but it actually acts as a nice little recap. The idea that triangles are similar. That word similar, if they have the same angles. Same angles mean same shape. So triangles that have the same shape, or they have the same shape if they have the same angles. And what does that mean for us with regards to similar triangles and their side lengths? We know that their side lengths are proportional. That's what we've used so far to be able to find those missing sides. Okay, one other issue dealing with a diagram and then some labeling stuff. I want you to take a look at the triangles that you see on the screen, because this happens to be one of those diagrams that is going to pop up over and over again as you work your way through your high school math. It also happens to be one of the triangles that can cause you guys some problems from time to time. And I don't know if it's quite an optics thing. You know, the fact that we really have like one triangle entirely inside the other triangle. But I want you to take a look and hopefully you can identify your 2 triangles in that diagram. I'm going to label them over off on the side. On the left, I have this big outside triangle, triangle DEA. And I'm hoping that you can see that. Triangle D, up to E, down to A. I enclose that shape. There is my big triangle. But I would hope that you can also see triangle BCA. Up to C, down to A, back to B. I've asked you to name the corresponding sides for the similar triangle. But notice I didn't give you really any angle markers. So what allows me to state that those things are similar? Well, I'm hoping you can take a look at the 2 triangles I've just highlighted and we can recognize a couple quick things. First off, I have told you, and that was really sloppy, that those are both right triangles. So we can see that they both have a 90-degree angle. What I'd also like to highlight for you then is they also have angle A in both. And so just like we spoke before, if I have 2 triangles that have 2 of the same angles in them, then by definition, that third angle must be the same. So maybe you can now see on that diagram that those are similar triangles. They have corresponding sides. Okay, for us to label them, I've asked you to name them. So within that, maybe we use our endpoints to label. So I could end up saying, if I looked at my angle markers, let's focus in on my green angles and my purple angles. That means on triangle DEA, that would be side length DE. Well, side DE on my big triangle would correspond with side BC. Those ones are connected, corresponding sides. If you then rotated around your triangle maybe now we look at the purple angle marker with the pink. Well, purple would be EA, to pink, sorry, would be EA on the big triangle. That would then correspond between the purple and the pink on the smaller triangle, CA. And then you take a look on the bottom. The bottom tends to be one that can be a little difficult to see just because the triangle is embedded in the other one. But my outside length of DA on the bottom would have to correspond with the shorter distance on the bottom of BA. You are going to see that triangle pop up over and over and over again. And in fact, what we're going to deal with for the rest of the unit really pertains to that diagram. So I want to make sure that we're good to be able to identify our corresponding sides. We probably took longer on that than what we needed to, but I could not stress the importance of it. Okay, one last thing I want to discuss. If we take a look at the triangle in front of us, triangle ABC, we have some labeling issues that we need to discuss. In grade 9, you should have gone through and discussed how to properly label triangles. And when we are given a single triangle, there's actually a different way that we name that side and angle within the triangle. Triangles have not a unique property, but they do have a very important property, which is every angle has a corresponding opposite side. Every side has a corresponding opposite angle. So for instance, if I just asked you to zero in on angle A, there's vertex A that I've labeled down in the bottom left corner. So if I was to call then angle A would be that angle. You notice across from angle A, there is only one side. This side over here. Quickly look down below the diagram. If I was to give you a rectangle, let's say, and I said, there's angle A. Well, which side is across from angle A? You now start to go, oh, well, obviously, well, I don't know, like, isn't that one also across? That you happen to have two sides that are across, not one. That's what's somewhat special about your triangle. That every angle only has one side across from it. Every side only has one angle across from it. And because of that, we use specific labels. So I'm going to go ahead and I'm going to get rid of that red you see on the diagram because, in essence, we've already labeled all of our angles. We label them based on the vertex. So if you wanted to, you could formally write in, like in that spot, that is angle A. That is angle B. That is angle C. You never have to write them in there. By definition, the label of the vertex labels your angle. Angles are uppercase letters. Okay, well, let's zero in on angle A. Angle A has one opposite side. And if I was to continue that arrow on, I'm hoping we can see, it takes us to the far side. Well, angle A has one opposite side. That means that side is called A. But if I just wrote A, now that labeling system kind of stinks because I can't tell those two things apart. So our rule for labeling, our language says, angles are uppercase, sides are lowercase. So if I was to erase that now in my diagram, there we go. We can clearly see angle A is already labeled by the vertex. Its corresponding side is the side opposite. There's side A. Very quickly around the shape then, we could say, well, if that's B, then its side must be opposite, so there's B. We could then say, there's angle C, its side opposite, there is C. And that is how we label our triangles. Uppercase labels for angles, lowercase for sides. That is going to be the way that we go through and we label all of our triangles now. Okay, your job to get ready for the next day. Jump in and get some practice on your similar triangles. Make sure we really, really understand the idea that our angles, if equal, create triangles that are the same shape. And because of that, their sides are proportional. And if we're good with that property, then you guys should be set up really well for the rest of the unit. Okay, best of luck.